about, or what this do? Yeah, this was saying, here's some graph of f of x on some interval a to b, drawn in rectangles, and add up all the signed areas. We say signed area because if this is negative, you're subtracting. That's when you're below the x-axis. So this was the signed area based on using in rectangles. So it was an approximation, right? And the goal was to approximate the area under the graph, between the graph and the x-axis from A to B. So the idea was if you use interlimiting rectangles, you'd get the exact area. So if we can take this limit, we now know the value or the area. The new thing is, it's really a pain to say find the signed area between the function f and the x-axis on the interval a to b. I don't want to say that all the time. So really, this whole section, or the big idea, is this new notation. Anytime we write this, it's called an integral symbol. So integral a to b, f of x dx. It's kind of like when we take the limit, the delta x becomes a dx. And this summation gets stretched out to become this integration symbol. All right. So when we take the limits and goes to infinity, we get the exact signed area. We give it notationally this value. This represents the signed area for f of x on the interval a to b. All right, it's all just notation. All right. Of course, there's a question: does this limit exist? Kind of like when we did derivatives, you had the difference quotient. You had to take the limit. If you had something like a corner, that limit didn't exist. Ends up for most functions f, this does exist. I don't know if most is the right word, but anything continuous, any nice function, it's guaranteed to exist. It also works for certain non-continuous functions. Even works for some that have vertical asymptotes. So that won't always happen, but overall, most functions, or especially anything we deal with, these are nice functions, this exists. All right. If the limit exists, we say f is integrable. So instead of saying differentiable, it's integrable. Notationally, f is called the integrand. These are the limits of integration, a, b, the interval you're on. Dx is called a differential. Yes. All right. And remember, this represents the signed area. If you haven't noticed, I do want to mention this. I've sent it by email, but who reads email? In chapter 4, because these are a little bit less comprehensive, I have been posting the files that I use for the examples I do in class. And the relevant thing there is that it has links to the websites that I mentioned. That doesn't mean for your homework only use the website, like you still have to show work. But it's a good way to check sometimes. It's a guaranteed calculator. All right, so that's that part. The other part of it, I also post my solutions. So these files have several examples in them. I post the written solutions. So this isn't exactly what I write on the board, but if you're looking at the two files, it looks like I covered what I was supposed to. So like you can see these from last time we did this. All right. You can also see when I don't follow my lesson plan at all. All right, so like later I'll post this file. It also has a couple more links that are kind of the same thing. If you load one of these, it's the definite integral calculator. So you can update the function, you can say which method you want to use, but now you know what this word definite integral means. So this thing here is called a definite integral. A definite integral is just a number. Later we'll talk about indefinite integrals are functions, actually classes of functions. For now, when we talk about definite integrals, it's a number, it represents a signed area, or net signed area. All right. So like in these examples, when you click definite integral, it tells you the exact value. All right. And there's a couple links for this. So I did want to mention that just in case you haven't looked at those as additional resources. I'll mention these real quick. We'll use these as we go at times. But now we have these things called definite integrals that are based on limits and sums. We can then mention certain properties. So what would be the integral from a to a? 0. Why is it 0? Let's think about, what does this represent? Here's some function f of x. Here's the number a. What's the area of this? The rectangle with 0 width. So area 0. In order to have any signed area, I really want to have some function b over here to get some width involved, right? So you just go a to a, you get 0. What are some other nice ones here? We can factor out, what happens if you switch the balance, a to b or b to a? A to b says we work left to right. What happens when you decide to work right to left? The way you think of this one is your delta x changes sign, right? Instead of b minus a, it would be a minus b. What happens there? It becomes negative. That's what happens here. The negative sign pops up. What about this one? What is this saying you can do? This is actually a little bit similar to what you do with the rectangles already. What if I pick a number C in the middle here? I could find that area and this area and then add them together. And that would be the same as finding the area all the way from A to B. So we have this property that says pick a number in the middle. I could find this definite integral, I could find this definite integral, and just add values together. Why might I want to do that? So we mentioned this works for f continuous. It also works for f discontinuous. What if I had a function like this? I could do this definite integral, and then I could do this definite integral, and find these two separately. So it's a natural way, like, why would I want to break it in the middle? Maybe having discontinuity or something. So then I can handle a nice thing over here, a nice thing over here, and go from there. Because we're doing area, remember, a lot of these, you can draw a picture and visualize the area. Once you know the graph, you can actually draw this and look at it. Almost, in some ways, it's easier to see than slow. And then this one says if you're adding two functions, you can just find the definite integral of each and add them. We're kind of used to doing things like that. You can take a constant out. You can never move an x outside the integral symbol. But just a number k, I could move outside. All right. So we'll do an example of some of these properties in a little bit, but I wanted to kind of mention them. The other one, we actually know some shortcuts here that we give you in this section. We'll tell you where these come from 2 or 3 sections down the road. But for now, we have a few shortcuts. If I'm integrating a constant, why would this make sense as the definite integral? Yeah. Here's some constant c. Here are my endpoints, a and b. Here's the x-axis. I want to find this value, which is just c times b minus a. These are a little bit more surprising. If I want to integrate x, I get this value. If I want to integrate x squared, I get this. All right, any questions so far? So we have this new notation, and we know it represents this thing we've been approximating. Now we say the exact value is called a definite integral. All right, it's when you take in rectangles and send into infinity, you get these values. Yes?
Well, but I mean, it makes perfect sense because you're basically doing the reverse power and inverse of the power rule.
Well, yes, but that's only if you know the fundamental theorem of calculus. We're getting there in 4, 5, 4, 6, something like that. It is related to derivatives. What is the derivative of 1/2 x squared?
X?
X. This is 1/2 times a number squared minus a number squared. There's a reason. There's a reason this comes in chapter 4. If you know how to take derivatives, if you work backwards, you can find areas. It's called the fundamental theorem. It's a great shortcut, and we'll get there. All right. So that's where we're headed a little bit. It's also an overview of what we care about in this section. Today I want to do a very long example in 2 ways. The shortcut way and the full, and when we do all the work. So let's say I want to evaluate the definite integral from -1 to 3 of the function x squared plus 4x. So there's a couple of problems in the homework like this, and it's similar to some limits and things you did back in 4.1. So, and really 4.3 is putting everything in 4.1, 4.2 together. We're giving it this new notation, but it's really taking what you've already done and putting it together. Right? So what does this represent?
Assigned area or x squared.
That assigned area. All right. You already graphed this. It looks roughly like this. So this is the function x squared plus 4x. Which means what? From here to here, I'd get a positive number. From here to here, I'd get a negative number. So my value would be this value minus this value. Whatever this area is, subtract it from this area. Do I think that's going to be positive or negative? Yeah, this region looks bigger than this region. So I expect this to be positive. All right. So number 1, by definition. Which means, what is my definition? My definition says it's the integral from a to b fx dx is equal to, the limit is then goes to infinity of my Riemann sum. Okay. That is the official definition, kind of like when we did the official definition of a derivative, it was the limit for the difference quotient. Now when I say what is this definite integral, it's take your Riemann sum, find the limit, and then goes to infinity. This is, I believe, the last section where you ever do this. Because what do we do for derivatives? We did it by definition, everybody complained, and we learned shortcuts. Chapter 4 is similar. Yes?
How do you know what n is? Like in.
And I just into infinity. So what happens here? What does it mean when you take a limit? What do you eventually do? Plug in that number in. So I plug in infinity for the number n. At that point, is there an n anymore? No, this part actually doesn't depend on n because when I take the limit, I get rid of the n. When I take this value, that only depends on n, right? So this depends on n. When I take the limit, it no longer depends on n. Hopefully I get just a number. Would it make sense that this is eventually just a number independent of n?
Right.
Yes, if that number represents this fixed quantity. So like this limit has to be a number. Eventually when you take the limit, the n goes away. So it's really just kind of a symbolic choice in it. Alright, so how do we do this? First I need this part, right? So what's delta x?
3 minus -1 divided by 10.
Alright, I'm going to do this part first. Why does that matter? What do I divide by?
N?
And this says eventually let n equal, or n go to infinity, but inside here, n is just a fixed number, right? So I divide by n. So this would be 4 divided by n. What should I choose for, or what's my value for xk? A plus k delta x. Start at your left endpoint, move k units to the right. So -1 plus 4k divided by n. Now the bonus question. What is xk star? In my formula, I know what f is, I now know what delta x is. I need an xk star.
Wouldn't it be somewhere between the interval of A and B?
It'll be on the kth interval, which is inside the interval AB. What should I choose for xk star? This is really a trick, in some sense, a trick question. Did I tell you which method we're using for the Riemann sum? We had several Riemann sum values, right? We could do a right endpoint method, left endpoint method, midpoint method. Trapezoidal technically wasn't one, but we'll pretend.
If it's infinitely small, why does it matter?
It doesn't. When we say this limit exists, there's a bigger technicality that says this exists whenever we choose xk star in the interval xk minus 1 to xk for any choice. For any choice xk star. I can do a left sum, I can do a right sum, I can do anything in between, I can do upper sums, I can do lower sums. That part doesn't matter. So really when we say this limit exists to give this definite interval, it's independent of how we choose the Riemann sum. What does that mean for us if we want to do this by definition? We're going to assume this limit exists. We're going to assume f is integrable, which means do I have to account for all possible choices? If we know the limit exists for any possible choice, what should we do? Take a choice that makes it easy. We can choose. So which one should I do? The easiest one is always just let it be xk, right? What does that correspond to? Xk is always my right endpoint. So this is really a right endpoint method. There's no reason not to choose the right endpoint method. If it works for any method, might as well do the one where all the indices work out nicely. Otherwise, this part's a little bit more of a pain because I have to do k minus 1. Alright, so then what is f of xk star? That's the same as f of xk. So f of -1 plus 4 over n, 4k over n. So what is that? X squared plus 4 times x. So I'm plugging this input into the function f.
But we still don't have N?
Hmm?
But we still don't have N?
Not yet. So I'm only looking at this box part where n is just a simpler letter that I'm carrying along. Right now, n represents a big integer. And that's all I need to know about it. Alright? So this depends on n is just a big integer. So what should I do now? So it's a little bit misleading. So in the notes, I wrote this as one big thing. I'm not explaining it. I wrote the full solution. So definitely look at those later, how it's written. But eventually, I'm only looking at this. Eventually I want to take the sum. What sums do we know? Add up 1 or k squared or k cubed. Those are the ones that we knew back in 4.1. Those are still the only ones we actually know. So I'm going to make this look like those, which really just means I'm going to expand everything. So if I expand everything, I'll get 1 minus 2 times 4k over n plus 16k squared over n squared minus 4 plus 16k over n. So clean this up. 1 minus 4 is -3 minus 8k over n plus 16k over n plus 16k squared over n squared. So 16 minus 8 is 8. So I get this. And you'll see why we need that in a second. But my goal is to write it as basically 1k, k squared. I want those to be just k to a power. So now that I have that, now we're ready to do a little bit more. I want to take the sum from k equal 1 to n of f of x k star times delta x. So we just found this value. That value is what we have at the bottom of the board there. -3 plus 8 over nk plus 16 over n squared k squared times delta x. What was delta x? 4 divided by n. Right. So I get this. -12 divided by n plus 32 divided by n squared times k plus, what's 16 times 4?
64.
64 over n cubed times k squared. So I get this plus, so I can always move anything outside of sum. It doesn't depend on k, right? So like this one, 32 over n squared times k, I can move the 32 over n squared outside and just have some k. Is this looking a little bit like those homework problems you really did not like in section 1? I only assume you like those. Right, does that step make sense? Now what do I do? Yeah, we know formulas for all 3 of these, right? Why did I do all this? Because I know these 3 formulas. And the good news, I give you those formulas always. You don't need to memorize those. So, let's see if I have memorized. What's the first one?
N times n minus 1 divided by
Almost. That one's in. But what's the next one? Now we're getting 3 times n times n plus 1 over 2. And then what's the third one? Alright, so I don't need to give you these. You accidentally memorize them?
Alright, did you leave it up on
plus? Alright, so I can't think of many other courses where that could ever come up. You tell them the cool way you come up with this? No, no. Oh, well. That's good reason. You don't have to remember, just be really confident when you say whatever. People believe the confident person. Alright, so that one ends cancel, that one's nice. What else? 32 over 2, that would give me 16.
And then you can also take one of the ends out.
N plus 1. N divided by n squared, that's an n on the bottom. Plus, what's 64 over 6?
It's 32 over 3.
32 over 3? Yeah, that's simplified, right? 32 over 3 times what? One of the n's cancels, and then I'm left with n plus 1 times 2n plus 1. So, keep going. My goal is, what is my eventual goal here? How far do I go?
Take the, like, infinity?
I eventually want to send into infinity, right? Things like this would be infinity divided by infinity. So, really I want to simplify even further, or make it look a little nicer. What happens here? That'd be plus 16, n divided by n, plus 16 over n. Now what about the other one? I can expand the top, that would give me 2n squared. Plus 3n plus 1. All divided by n squared. So negative 12 plus 16 plus 16 over n plus 32 over 3 times 2 plus 3 over n plus 1 over n squared. So negative 12 plus 16 is 4. Alright, 64 over 3.
Mm-hmm.
Plus 3's cancel out, so 32 over n plus 32 over 3n squared. What's 64 divided by 3?
A decimal.
A decimal. Actually, no, that's good because I know the answer is a fraction.
Couldn't you also combine the 32 over n and the 16 over n?
So this would be 12 plus 64. Plus 16 plus 32 is what? 48. Plus 32 over 3n squared. So 64 plus 12. 76.
Right.
Alright, this is fully simplified as far as I can. Yes?
Where did you get 12 plus 64?
This one. 4 is 12 divided by 3.
Oh.
Alright. Now what? If you do a problem long enough, nobody knows what you're going for.
And now you got it. And
Now I put it
maybe.
in there. So my goal is to find the limit. I wanted to find the integral from negative 1 to 3 of x squared plus 4x. And we said this is the same as the limit as n goes to infinity of this. Why can I drop the star? It's the same as the limit for the right-hand sum. Right-hand sum has to work. So I can just pick a method, right? Pick any Riemann sum. We always pick the right handful. So then what is that? That's the limit as n goes to infinity of what did I find? All of that is equal to this. 76 over 3 plus 48 over n plus 32 over 3n. So what do I get? 76 over 3 plus
0,
48 over infinity is
0.
0. This one's also 0. All right. That area is exactly 76 over 3. And I should say signed area, right? It had a positive part and a negative part. Hey, you didn't have to like take out a calculator and add a bunch of times. It's not really a consolation prize. Like as much as you hated doing 6 rectangles, now you miss doing 6 rectangles. One was tedious, but draw a picture, you can resolve. This one's tedious and then more tedious. Alright, so that was the example I had planned for half the day. And we're not done with it yet. That was part 1. Part 2. Use shortcuts. So I want to find the integral from -1 to 3 of x squared plus 4x. What my shortcut say? I can break this apart into other problems. So what do I mean by shortcuts? We had 3 or 4 formulas. You're not going to be able to read this probably. But we had these 3 formulas. Yeah, you can't read that at all. We have these 3 formulas where we know the definite integral. I want to use those 3. Okay? So that's what I mean by a shortcut.
These didn't need to be memorized, we didn't get those.
Nope. But
And
they don't need to be memorized for a different reason.
are we
The other ones don't need to be memorized because I give them to you. These don't need to be memorized because by the time we take the test, you'll know how to derive them with no effort. Yes?
and are we gonna be allowed to use the shortcuts on the homework?
It's based on directions. I think there's 1 or 2 problems where it says use the definition.
But as long as it doesn't say that,
But
we
if it
can
doesn't
use.
specify you need a definition, use a shortcut.
Okay.
Unless you can't use a shortcut. What happens there's another whole block of homework problems where you can't use shortcuts. So, we talked about an example like this yesterday. I'll go through that in a minute. What if I asked you to find this? Do we have a shortcut for that? The shortcuts were if my integrand was 1x or x squared. So do I have a shortcut? No. But there is a shortcut. It's just not one of the formulas. What is it? It's a semicircle. What does this represent? We're supposed to find
Half the units, the top
the net
half
signed area
of the unit circle.
from -1 to 1 of this, right? So what is that?
Half of pi r squared.
Area of a circle is what? Pi r squared?
Yeah, and then
So pi times 1 is pi. Only a half the circle. Pi over 2. I don't need any rectangles. Please don't do rectangles. Technically, if you send the limit as n goes to infinity, it works, but it's not going to be one of the 4 formulas we gave you for sums. So even then, you can't use any of the formulas we gave you. If you could use the formulas we gave you, it would be the same as using the shortcuts we gave you formulas for. Is how do you think you come up with the formulas for those definite integrals we gave you?
the derivative.
If if you look at the sum, so we gave you ones like this. Give you a formula for this. If you do a right hand rule and expand it, basically on x squared, it's going to start looking like this, where I can use these formulas because I know these. But it's because I'm only going to get things like 1k, k squared, k cubed. Once I get past those, I don't have any formulas, do I? Guess which ones correspond to those formulas. The integral of x, x squared, or 1, or I guess x cubed. Once you get past those, we don't give you formulas because we can't derive them in this section, so we know other results. So, if you can do it by hand, you can also do a shortcut. Anything like this, we've not given you enough content to actually do that. Unless you do geometry or kind of habitual. When you draw the graph, you know what it is, you can find the area. So those are our 3 techniques. Really, it's 2 techniques. Alright, so how would I do this one using formulas? That's the same as, I can treat it as this integral plus 4 times this integral. So those kind of definite integral rules we have where you can break them apart. If I'm adding 2 things, I can just add the 2 integrals. If I have a number 4, that's constant value, so I can move it outside. If this has an x, that means nothing with an x can move outside. So then what is this? We said this one is 1/3 times b cubed minus a cubed. And this one is what? 1/2 times b squared minus a squared. 5 formulas. So what do I get? 1/3 times 3 cubed minus -1 cubed plus 2 times 3 squared minus -1 squared. So what is that? 9 plus 1/3 plus 18 minus 2. So 25 plus 1/3, which would be 75 plus 1/3, so 76/3. You're going to get really good at fractions. Chapter 4 is like final exam in arithmetic. 2/3 of every problem will just be arithmetic. 1/3 calculus, 2/3 arithmetic. You go to check your answer in the back of the book and it's a number and your number's not quite the same and it's sad. Like, you know, the answer was a function, you could see which term was wrong maybe. Now you go to the back of the book and the answer is 76/3 and you get a different fraction and it's not clear if you made a mistake on the calculus or you just plugged in wrong. And when half your page is arithmetic and plugging in and trying not to lose negative signs. Any questions on that? See, I like the shortcut. Usually a thing.
Will we have the use of definition on sentences? Do we even have the time?
You'll have one problem on the definition and it's going to be one that will not take that long. When I say that long, I'm referring to what we just. So what made this one so awful? Everything. I had to do xk squared, right? What was the problem with xk squared? Xk was the sum. What would have made that much easier?
If it was 1 instead of
If a was equal to 0. What happened if a was equal to 0?
It would just be 4K
It
over
would have
it.
been 4K over in. 4K over in would have been a lot easier to plug in and simplify. There's ways to make this a lot shorter. You're probably gonna have 0 as left endpoint. Based on the history of me writing exams for this that are doable. Hopefully doable. Right. So like this is, anytime you have to expand everything, that's gonna be worst case scenario for these. Alright, I have 2 more examples, but we can always do those on Monday. We're gonna finish this topic on Monday. One of them is more like this idea. That'll give you a piecewise function. But when you graph, you get triangles, so not too bad. And then the other is using more properties like this. So we'll definitely do that on Monday. And then answer our homework questions. So make sure you look at this over the weekend. Probably try to finish this homework. The worst part is going to be this. It's not going to be every time though. Alright, a lot of the blocks are more draw a graph and then do something like it's a circle, triangle, rectangle, formulas that we know. Okay. Any other questions? If you haven't turned it in, make sure you give me your prep assignment. And if you didn't finish the 4-2 homework, make sure you get that uploaded.